So decision tree. The way that I want to explain the decision tree is I'm gonna use these examples to explain it. So support is again is decision tree is supervised. So we do have accent corresponding labels. And let me see. We have 4 features. So you can X1 and X2, 3 and 4. These are the inputs. And this is why it's the output or labels. And assume that you your factory is gonna make some product. And 4 different factors, and eventually it's gonna have influence on whether your product is good or bad. Okay, that's the inputs and outputs. With that, let me see for feature 2, we don't know what it is, but don't worry about the kind of physical meanings, but say this is yes, and these are no and yes. And feature 3, maybe like temperature or whatever. So it's low, high, or medium. So it's 3 different levels and these 2. And feature 4, again, is mediums, high, low. I don't know what it, but say you can think it's kind of level of pressure, whatever. And for feature 1 is very interesting. Say we have yes and no, and this, the question mark is that say maybe this information is not available or we don't know. So I put question mark, or we forgot to measure the whatever, any kind of situations. So these are the informations or training data set that we have. And we also know corresponding outputs. Based on this, I want to create the classification models. It's a classification problems. And the best thing is that I want to see, say, if I use this one, probably yes for feature 2 is bad. It's good. And it's no, no, no. Good, good, good. But yes and bad, the thing is these 2 are different. Or you can try others as well. So the conclusion that we can make out of this is that actually if feature 2 is, I guess, is highly related to, but not 100%. That means we have to consider other factors as well, but we don't know how. Okay, that's so. Let's follow the. So let me see feature test. What do you mean by feature test? Test in the first levels, and I want to pick the feature 1 and 3 different. We have question mark. That means we don't know, and yes and no. So let me circulate this. The corresponding, we have bad and good and good and bad. So we have 2 good and 2 bad, right? I'm just simple counting process. And for yes, we do have yes here, and bad and bad, bad. Oh, this is good. So at least we can see there's a for feature 1, if that's yes, all of them are bad. All of them are bad. So somehow related, we can guess. If it's no, right here, we have only 1, it's good. Okay. So if, let me say, if feature 1 is, if that's it, to be a good candidate, to be a good feature, or to be a good factor to make right decision or right predictions on the outputs. This is good, right? And this is good. Because if this feature one is yes, at least for training data set, we can make conclusion that is all of them are bad. If no, all of them are good. But the problem is if we didn't measure it, it's half and half. Half and half. I'm gonna show you what it is in a minute. So I guess feature one is pretty good, but let's try feature two as well. For feature two, we have yes and no. So we have yes and no. And see, yes, bad, bad, bad. And we have no's and good, 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 bad, and like that. Okay. Now you can guess what it is. That's the number that fully separated by feature two. So 3. And over here we have 3 and 1. So 4 of them are fully separated or classified by feature 1. And we can repeat the same thing for the feature 3 and feature 4. Okay. Now I'm going to show. So at least for the first level, which feature is the best? Which feature is the best when it comes to classification?
1.
Right? It's obvious, right? Because among how many? Among 8, 4 of them are separated. 4 of them are separated. So we can say that feature 1 is the best, at least for the first level. So we're gonna erase that. So, but the thing is that this is not separable, so we have to utilize other features as well. So move to on the second levels. So that means that for first levels, we have 4 of them, 3 and 1 of them are separated. So let me show you the animations. So these are classified, already classified for in the first level. So we don't need to worry about at all. So in that case, in second level is that we ignore that because it's already separated. So only 4 of them. This is the problematic. So let me, for feature 2, because we already used that, so we don't need, we cannot use that. Feature 2, yes and no. And if yes, bad. If no, good. Oh, which is okay. So in that case, good. And we can see others as well. So which one you're gonna pick? Which features that you're gonna pick for second level? It's too obvious that, right? Because 4 of them, all of them are separated. So, and I'm gonna combine them together. So I'm gonna move that to this way. So that's the decision tree. Because looks like trees. That's how the name comes, name after. So let me summarize this guy. So if we build a decision trees, that means actually it turns out we don't need these 2 features. which is good. Instead of we have 4 features, it turns out that out of the decision tree, we can think of only 2 of them, which is feature 1 and feature 2 has actual impact on the output. Only 2 of them. Okay, that's another information that we can get out of decision tree. And the thing is, let's check the feature 1 first. Then we good and good. And if somehow if you don't have any measurement, and for feature 2, yes and no, and we can good. And as you can see, all the separated. So let me ask then, which features are the most important? Feature 1 or feature 2? We know that this has nothing to do with predicting the output. So we can neglect or we can remove them. It's not important at all. But feature 1 and feature 2, which one you guys think is more important? Feature 1, right? So in decision tree, whenever here is the most important features. So another outcome out of decision tree is that we can tell that which features we can tell feature importance. This is classification models, of course. So it's the original goal is that whenever given inputs, we have to classify them. That's the first thing. But for decision trees, another information that we can get out of is that we kind of know that which features are more important than others. So it's a feature importance. Okay, but there's some issues on that. What kind of issues that we have that here is that what if? It's the homogeneous, that means these are the homogeneous. Separable. Here the example that we have is only 8 data points, so in most cases, but suppose we have like 1,000 or 100,000 data points, and in the outliers and noise on it, there are whole kind of things gonna happen. So in that case, in most cases, zero homogeneity is extremely difficult to achieve. Here, so far what we did, just count it, right? We just counted it for homogeneous set. But for big data set, that's gonna unlikely it's gonna happen. Unlikely it's not gonna happen. So we have to come up with a different concept. Here, disorder. So that's the definition of disorder. I'm gonna show you and explain what it is in a minute. But before that, let me ask, you guys look familiar or not? This one, the equation that we have. You guys, you think this has seen it before somewhere, or this is completely first time that you see this kind of things?
Yeah, this is a logistic regression.
Right. It's you see that it's in the logistic when you discuss logistic regression, or we can say it's cross entropy, whatever. So it's related. Okay. And that's, I'm going to in cross entropy. And let's keep that in mind. I'm going to revisit and explain it, why it's related in detail. But let's just take it. Okay, so someone said this is definition of disorder. That's okay. I'm just going to take it. And I can plot this x. And from 0 to 1, you have like 0.5. When you say, when x is like half, let me compute it. Okay, so this one is, so it's when x d is equal to 1, when x is equal to 0 or 1, almost 0. And the way this is, let's say we have good and bad and total. If we do that, so it's a good over total is x. And when x is 0 means that all of them are bad. And x is 1, that means all of them are good. So for classification problems, like I said, these are good, right? If we are able to separate them, that means that these are the good case. It's good for classification. So good, I mean, for classifications, I mean, here is a disorder, but order is good. That means that we can separate them. On the other hand, when x is, this means that in total, half of them are good or half of them are bad. It's not ordered, it's disordered. That's why we have maximum number, which is 1 in this case. The highest values in terms of disorder. So for classifications, you want to maximize disorder or you want to minimize disorder? I want to minimize that. I want to minimize the concept of disorder. So let's compute. Let's go get back to decision trees. And another, so this is disorder of the single set. And let me explain with this example that for feature 1, we have, for yes, we got that one. And disorder is equal to 0, right? Because it's ordered, and this is ordered, and it's half and half, so d is equal to 1. So that's kind of that we can compute it. We can compute the disorder for each set, and just to math based on this definition of disorder. But here we have 4 product and 3 product and 1 product. Like that. We have total 8 and 4 of them. We have total 8, 3 of them. We have total 8, we have only 1 of them belongs to each set. we're gonna use this as a weight to compute quality of test, which means that if you use a feature 1, the quality of test is like, so we have this order is 1 and zeros, and the weight. So that's the quality of the test. So Q. Okay. Then we can do, for feature 1, we can compute quality of test. And for feature 2, repeat it and quality of test, like that and like that. So in the previous ways, we have to count it, right? So in that case, we have to pick the maximum case. But here is a definition of disorder. So we have to pick the smallest one. We have to pick the smallest one. Okay. And for second, we have to and this is the best. This means that there is no disorder. All of them are ordered. That means all of them are it can be classified, so like that. Okay. So instead of just counting the data points that are classified by features, we're gonna use the concept of disorder or quality and the quality of test. That kind of we're gonna use that kind of metric to pick which features are in decision tree process. This is going to be more effective, especially if you have the training data points that have outliers and noise and big data set, because it can handle those kind of noise effect as well. Then let's go, because I said I'm going to revisit the cross entropy concept. So in decision tree, so again, think about the cross entropy, why we have, I guess in that over there it was like you remember that kind of thing, probabilities. P is also in for logistic regressions, is the probabilities, the p-value is from 0 to 1. So that's cross entropy is it was that it's metric for disordered. So for logistic in the logistic regressions, we're gonna find out linear boundaries that minimize the disorder. That's why we have in decision tree and logistic regressions, we have the equation that we have, because it's going to give it's the same concept. I want you guys like really kind of get some insight or concepts of disorders here. So go back to logistic regressions, why we have that kind of the loss functions or objective functions. All the concepts are related. Okay. Now let's move on to how do you implement it? Actually, you can program it, but again, it's already the function exists in sklearn. and tree.decision tree classifier, and use a criteria is the entropy concept. And there are many different options that you can pick. And for each the criteria, you can Google it, and I don't think that's you guys can easily understand. And maximum depth 3. Actually, you can design it and fit. And that's what we got. And this is what Python provide for us. We can do nonlinear classifications as well using decision tree. Suppose we have 2 inputs or 2 features and apply the decision tree. And let me ask, what kind of boundary that you're gonna get out of decision tree? Okay, so suppose we have that. In say logistic regressions, and given such kind of data points distributed or training data points distributed, most likely we're going to have this kind of these classification boundaries. To build up this, we have to think x of 1, x of 2 at the same time. But for decision tree, we're not going to think of 2 or multiple features at the same time. We're going to only think about single features. So single features. And once we're done with that, another feature. Which means that for classification boundary, this is the only thing that we can have. Because if that's that's the only thing that we can do. For feature 2, this is the only the classification boundary that we can have. But we can apply for decision tree, we can apply each boundaries in sequence. So with that in your mind, and imagine what kind of classification boundary that we can get out of decision tree in this case. We know that SVM or logistic regression is like that, but this is what we can get out of decision tree. All the decision boundary should be parallel to the axis. We're not going to have this kind of boundaries. We cannot. We have to have this always. I guess you know why now at this moment. I mean, this is really important to think or understand the mechanism inside the decision tree. And for multi-class classification problems as well, again, what you think you have to see is that all the boundaries are parallel to the axis. We cannot have like this. in decision tree, we cannot. Since with that kind of restrictions, we have misclassified data points. How do you increase the performance of decision trees? Probably we can increase the depth then it's gonna be like that. You see what I'm doing it? So here, go back to this, the option that we have. Of course, if you increase that, it's kind of like overfitting problems. So you have to decide. But you can control whether you want to increase the classification performance in the training data set or like generalization things. The tuning parameters in the decision tree is maximum depth. You can control it. Okay. Another thing that I want to mention it here. Suppose you have, how do I say, this kind of data set. Somehow you decide to use a decision tree for classification, then probably your model is like that, right? But what I'm gonna do, I'm gonna rotate it. I'm gonna use coordinate transformations. Say I'm gonna rotate it, then say U1 and U2. I do some kind of linear transformations, then apply the decision tree, done. You don't need think about any features related to U of 1, only like values like threshold is greater than or smaller than, we can do classifications. Okay. So for classifications, no decision trees, decision boundaries always should be like always parallel to the axis. So that's can be some, give us some limitations. Right? How to do that? How to avoid or overcome? You can increase the number of depth or think about coordinate transformations before you decide you apply the decision tree. Okay. And probably last thing is that we can do ensemble method. And this is like for either classifications or regressions or other tasks, we can do we can construct multiple decision trees. So like that, tree 1, tree 2, like that. And we do like, how do you combine them together? Like most the common thing is to majority votings, whatever. And we decide final decisions. That's ensemble method in general. But more specific for decision tree, if we do that, we call it random forest. So this is the ensemble version of decision tree. How do you implement it? That's it. Random forest classifiers. Okay. Then as you can see here, it's more like kind of things. Okay, so that's all the materials that I have for decision tree. And the reason that why I put the KNN and decision trees is it's a slight different from like software vector machines and logistic regression, things like that. It's non-parametric, but for me it's more natural way of thinking. It's more natural way. It's more reasonable or easy to understand. That's extremely good. I mean, when it comes to implement or utilize it, that's the one of the benefit that you can, I mean, for the decision tree, I mean, when the outcome of decision tree is that you kind of see that, okay, this is feature 1 and feature 3 and whatever you for each, then you can see that whether the input is like smaller or greater and smaller, greater. You kind of see what's happening and what's going on inside your model. So that you can trust more on your models, because you know that you understand what's going on inside. So that's kind of, it's more transparent. You can increase the reliability of your models. That's one of the biggest advantages that I can. That's why most people like use this kind of decision tree or KNN, although it's very easy or simple models. So they prefer to use simple models and more transparent models over more complicated and black box kind of models. Okay, so that's all I have